Have you ever wondered what a black hole actually looks like up close? Well, in this explainer, we're going to take a trip, a journey to visualize one of the most mysterious, most powerful objects in the entire universe. And we're going to use the latest science to see what is, by all accounts, completely unseeable. All right, so let's just jump right in. The whole question is a bit of a paradox, right? I mean, how on earth can you see something that's famous for swallowing light? Nothing escapes. But the answer? It's honestly more beautiful and frankly more bizarre than you could probably ever imagine. So, look, we obviously can't just hop in a spaceship and fly to a black hole. Not yet anyway. So our vision of them, what we think they look like, is really built from a combination of three key things. We've got these incredible observations from telescopes. We have the fundamental laws of physics, and then we have these amazingly powerful computer simulations. These are the things that really bring Einstein's most mind-bending theories to life, right on a screen. Okay, first things first, we have to get our heads around the most important part of any black hole, the event horizon. Now, this isn't some solid wall you'd crash into. Think of it more like an invisible line in space, a boundary. But it's the ultimate point of no return. Once you're past it, that's it. There's no coming back. It's what makes a black hole a black hole. And for the longest time, all of this stuff was just theory. It was all math on a blackboard. But then, pretty recently, something amazing happened. We finally made the leap from just pure imagination to actually seeing one. And it was all thanks to this incredible, revolutionary project that gave us our very first real glimpse. And that project is the Event Horizon Telescope, or the EHT. Now get this. By linking up radio telescopes all across the globe, scientists basically created a virtual telescope the size of planet Earth, an Earth-sized lens. And that was powerful enough to do the impossible, to take a picture of a black hole for the very first time. I mean, what a monumental achievement. Absolutely incredible. So what did the EHT show us? Well, it gave us images of not one, but two cosmic monsters. First up, there's M87 star. This thing is a supergiant, weighing in at 6.5 billion times the mass of our sun. And then there's Sagittarius A star, or SGRA for short. It's a lot smaller, but it's still a massive black hole, and it's right in the center of our galaxy, the Milky Way. The fact that we could capture both showed that our theories hold up, even at these wildly different scales. And just to give you a sense of scale here, that image of M87 star, the light that made that picture had been traveling for 55 million years just to get to us. Think about that. The sheer scale of this kind of cosmic photography is just, well, it's staggering. So when you look at that famous donut picture, what are you really seeing? Well, that bright glowing ring, that's not the black hole. That's actually superheated gas, plasma, swirling around it at incredible speeds. The dark spot in the middle, that's what we call the black hole's shadow. It's the region where light gets trapped for good. But here's the really wild part. Because gravity is bending light so much around it, that shadow we see actually looks about 2.5 times bigger than the event horizon itself. It's a gravitational illusion. All right, so seeing it from Earth, absolutely incredible. But that's just the start of our journey. Now, let's fire up the imagination and the computer simulators and get way, way closer. We're heading right up to the edge of that swirling, fiery inferno. This is the accretion disk. This is the thing that makes a black hole visible to us. You see, as all that gas and dust gets pulled in, it starts to spiral, and the friction and gravity are so intense that they heat the stuff up to millions of degrees. It becomes a glowing, incandescent band of plasma, shining brilliantly. But you'll notice the disk doesn't glow evenly. There's a reason for that. You know how an ambulance siren sounds higher pitched when it's coming at you and lower when it's going away? Well, the exact same thing happens with light here. The side of the disk that's spinning towards us looks way brighter, and even a little bluer. The side spinning away from us looks dimmer and a bit redder. It's an effect called Doppler beaming, and it's why one side of that ring is always so much more intense. Now, if all of this is starting to look a little familiar, well, it probably should. The movie Interstellar absolutely nailed this. They worked with the physicist Kip Thorne, a Nobel Prize winner, by the way, to create probably one of the most scientifically accurate pictures of a black hole we'd ever seen in fiction. And that movie illustrates one of the most beautiful and strange effects perfectly. The gravity is so powerful here that it's actually warping the fabric of space-time. It's literally bending light from the far side of the disk up, over, and around the black hole, creating that incredible halo. So think about that. You're seeing the front of the disk and the back of the disk all at the same time. It's just wild. Okay, let's push it. Let's get even closer. We're going to a place where our understanding of physics gets pushed to the absolute edge. A place where the view of the universe itself starts to, well, it starts to break. As you get this close, things get seriously weird. The halo of light gets impossibly bright, and that black shadow just grows and grows until it dominates everything. And then you notice the stars in the background. They start to streak and warp. Their light is being bent so much that you'll start seeing multiple images of the same star. Ghosts, really, as their light takes all these different crazy paths to get to your eyes. Okay, this is it. We're at the ultimate boundary, the event horizon, the point of no return. So, what happens now? What would you actually see if you took that final, irreversible plunge? And right away, here's the first major surprise. According to Einstein, for you, the person falling in, the moment you cross the event horizon is, well, it's nothing. No dramatic bang, no force field, no sudden jolt. From your point of view, it's a completely smooth, almost boringly calm transition. Now, your fate, that depends entirely on what kind of black hole you picked. If you fall into a smaller one, a stellar mass black hole, the tidal forces, the difference in gravity between your head and your feet, would be so extreme they'd tear you apart long before you even got to the horizon. They call it spaghettification, which is a pretty vivid, if gruesome, description. But if you chose a supermassive one, the curve of space-time is so gentle at the horizon that you could sail right across, completely intact. Okay, now we get to the really, truly mind-bending part. Time itself. For you, falling in, your watch just keeps ticking normally. A second is a second. But for anyone watching you from a safe distance, your journey would appear to slow and slow until you seem to freeze forever, right at the edge of the event horizon. From their perspective, while just a few moments pass for you, billions of years could fly by for the rest of the universe. So what's the very last thing you'd see? If you look forward into the black hole, the darkness just expands to consume your entire view. But if you were to look back, you'd see the entire history of the universe playing out behind you, compressed into a tiny, shrinking, blindingly bright circle of light, the entire cosmos squeezed into a single point. Wow. So after that incredible journey, let's pull it all back together. Let's take the real observations, the physics, the simulations, and paint one final clear picture. And this quote really says it all, doesn't it? Up close, a black hole isn't some kind of cosmic vacuum cleaner. It's not a swirling drain. It's a profound absence. A perfect circle of pure, utter darkness, surrounded by the most brilliantly bent and distorted light you could ever imagine. And I think it's so important to remember this. None of what we've talked about is just made-up science fiction. This entire journey, from the actual photos taken by the Event Horizon Telescope to the mind-blowing simulations run on supercomputers, it's all a visual tour of what Einstein's theory of general relativity actually predicts. It's a beautiful, bizarre, extreme, and very real part of our universe. You know, a journey like this really shows us that even the most mysterious, most extreme things in the cosmos can, eventually, be understood. And that just leaves you with one final thought, doesn't it? If we figured out how to take a picture of the invisible, what other incredible, unbelievable cosmic sights are out there, just waiting for us to build the eyes to see them?